Alright guys, so I decided to make you a video. I meant to do the implicit function theorem in class on Tuesday. Um, Ran out of time. We could talk about it tomorrow in class on Thursday, but we need to keep moving forward, and I don't want to spend too much time on this. So I thought I'd kind of quickly write things up here. I'll give you the Math 1410 treatment, give you some slides with some audio. We'll go through the details just so that we can throw this up here on the web, and you guys will be able. This way, also, you'll get it. You'll get this information a little bit sooner. You don't have to wait for class on Thursday. This maybe will help you with your the last problem on the assignment that's due Friday. Okay, so let's recap. We'll start with some things you know. Implicit differentiation. You know how this works in the sort of the Calc 1 setting, but you've probably seen implicit differentiation also in the context of several variables. It's usually covered in Calculus 4. Right? If here's kind of the classic example, right? The unit sphere, right? This is the unit sphere. The set of all points that are distance 1 from the origin in R3, right? So this is a subset here of R3. Right. And in general, for any sort of real valued function like this, if you consider a level set of this form, the level set is generally going to be some sort of surface that is kind of generically one dimension less than the space that you're working in. Given some conditions, of course, because you can come up with sort of badly behaved functions where the pre-image, you can come up with functions where the pre-image is empty. You can come up with functions where the pre-image is say a point. For example, if you considered for this same function, if you considered the level set for 0, right, there's only one point where f of x, y, z is equal to 0, and that's the origin. That's certainly not a sort of a surface sitting inside of R3. But with appropriate conditions, you can guarantee that you get some sort of nice surface. So the point is that, you can, at least in principle, solve for one of these variables in terms of the other. This is essentially what the implicit function theorem is going to do. Is even if we can't, in practice, solve for one of the variables in terms of the other, in theory it can be done. Right? Here we can do it explicitly. Right? We could say, for example, if z is bigger than 0, so for z between 0 and 1, strictly greater than 0, you could solve for z here. You could say, well, I can write z as the square root of 1 minus x squared minus y squared, right? So that works for x and y in some appropriate domain. In this case, right, so this would be some, g of xy, and that's going to work as long as xy belongs to the set of points where x squared plus y squared is strictly bigger than, well, I guess, but less than or equal to 1 and bigger than or equal to 0. I should have left myself some room. Let's make some room. 0, strictly less than x squared plus y squared, less than or equal to 1, right? And so now you've got this function g. You might want to calculate, say, the partial derivatives, dg dx, dg dy, and you probably kind of remember how this sort of thing goes. You start with, say, the equation x squared plus y squared plus z squared equals 1, and you take the partial derivative of both sides. So if I took, say, the x derivative of this thing, then I would get well, 2x dx dx plus 2y dy dx plus 2z dz dx. And of course that should be equal to 0. One of the things you got to be careful about when you're doing this implicit differentiation, there's a bit of a collision of notation here, which can lead to sort of incorrect assumptions. There's some kind of logical fallacies you can make if you're not careful. So one of the things that can go wrong is, well, this x, this y, and this z, these are sort of R3 variables, the x that you're taking the partial derivative with respect to here, that's an R2 variable. And so really what you're doing here, the right way to probably think about this is that maybe you're thinking about parameterizing or something. So maybe you're letting x equals u, y equals v, and z is equal to g of u and v. So you want to be able to say, well, dx is equal to 1, right? So you want to say, okay, so this this guy here is just going to be equal to 1. This guy here should be equal to 0, and then this guy here, well, you know, we don't want to think of z and x as independent variables anymore. We're thinking of z as depending on x, and so this last one here becomes dg dx. And so if you want to, you can solve for dg dx, and you get what do you get? You get that dg dx is equal to minus x over z, right? Or I mean, it was 2x over 2z, but we canceled the 2's. And so this is minus df dx over df dz. It's worth making a note of that. So you want to write down a theorem that kind of formalizes all of this, and that's the implicit function theorem. Here's the statement of the implicit function theorem. So the setup is you've got a smooth function. It's got to be at least continuously differentiable from Rn plus 1 to R. And you want to think of this Rn plus 1, you want to think of splitting it up into the Rn part and the R part. And label our points like so. So the first n variables, x1 up to xn, we sort of think of those as being separate from the last one. We're kind of doing this in the context that we're solving for the last variable. We're solving for the n plus first variable in terms of the other ones. We want to write z as a function of x1 up to xn, the same way we wrote z as a function of x and y in this example here. Of course, it doesn't have to be the last variable. It could be the first, it could be the second, it could be any one of the variables, but we're going to choose the last one for ease of exposition. And of course, you can always relabel your variables, so there's no real loss of generality here. So you define the pre-image of some real number a. So this is just a set of all points such that when you plug them into your function, you would get a, right? So f of xz is equal to a. And you look for a point in the pre-image where this final partial derivative is non-zero, right? Let me jump back to the one we were just doing. So you notice here that the z derivative for this function, you notice that, so df dz here is 2z, is non-zero as long as z is not equal to 0. So if I want to sort of define z as a function of x and y, I have to do it either for the upper hemisphere where z is positive or the lower hemisphere where z is negative. Along the equator, this wouldn't be valid. I'd have to solve for one of the other variables. I'd have to solve for, say, x as a function of y and z, or y as a function of x and z. But at any point on the sphere, at least one of those partial derivatives is going to be non-zero, and so you can treat that one as sort of your final coordinate. Okay, so if that partial derivative is not equal to 0, then you can define this last variable z as a function of the remaining variables, right? So really what we're saying here is we're saying that I can write z as a function of the variables x1 up to xn. This is what this condition is saying here, right? So it's saying that if you take, so this is a point here, so this is going to be, well, it is a point in this level set, right? But this is not necessarily something that works for, right? We see that here. This is not something that's going to work for the entire set, right? So it's maybe the same function doesn't work for all of S. maybe it only works for part of s, just as in the previous example, the function we wrote down only works for the sort of positive upper hemisphere, right, away from the equator. And so, different parts of your surface might need to be defined using different functions, but in principle, as long as you're on some piece of the surface, or you choose a point on the surface where an appropriate partial derivative is non-zero, then near that point, so that's when we say this open ball here and this interval here, this is just a way of saying we're not moving too far away from this point where this partial derivative is non-zero. As long as we stick around in a neighborhood of that point, then we can solve for the last variable in terms of the other ones. And if you think about this partial, if you look at the way you actually do the implicit differentiation to calculate the partial derivatives, right? The x derivative for g is the x derivative of f divided by the z derivative of f. Similarly, for the y derivative, you would replace your x's with y's here, right? So you take the partial derivatives, the kind of first n partial derivatives for f, and you divide them, you multiply by -1 over the final partial derivative, and that's how you solve for the g derivative. So that's what this notation is doing here. This subscript x here is just telling you that we're only considering the partial derivatives df dx1 up to df dxn, right? So I guess this is kind of more, this is maybe the right way to think about this is a partial derivative in the sense that it's not the whole derivative. The whole derivative would also include df dz. We're leaving that one out. We're including the first n partial derivatives. And if I want to calculate the corresponding partial derivatives for g, I take these partial derivatives, I multiply by -1 over that final partial derivative, and that gives me the g derivatives. Okay. So that's what the implicit function theorem is saying, right? And you can sort of sketch this out. The picture you should have in mind here is, sort of you have like I guess Rn plus 1 is here, R is here, and here's a piece of your surface, and so you find a point where, so here's your sort of your point x naught, z naught, right? And so, from this point of view, you're looking for a point where the tangent, if you like, is not vertical, where there's tangent line, tangent plane, right? This condition here is basically saying with respect to that, if we draw that final coordinate vertically, we don't want the tangent to be vertical. That's what allows us to solve for that final variable in terms of the others. And so then you can see, okay, well, I can kind of, I can drop this down, and I can find a little open ball around the shadow of that point in Rn. Sorry, not plus 1, just Rn there. And I can find a little interval. Oops, I'm still on eraser mode. A little interval around z naught there, and so then in this region here, you can see that, yeah, this piece here, I can think of that as a graph, right? So this point here, so if this is my x, then this is my z, which will be my g of x over here, right? So that's what the implicit function theorem is telling you. Okay, so we've mentioned this definition before. Oops, there was supposed to be a u. I don't know what happened to my u. So f will be a function from subset u in Rn plus 1 to R, right? And we say, what is a regular value? A regular value is one where the derivative has maximum rank for every point in the pre-image. And since we're dealing with a real valued function here, that means you're dealing with the case where the derivative is simply df dx1 down to df dx n plus 1, right? And so this n plus 1, that's your z, if you like, right? So this is non-zero, and that means that at every point. So what this is telling us here is that for every point x in the pre-image, at least one of the partial derivatives is non-zero, and so that means near that point you can solve for that variable, that xi variable, in terms of the remaining ones using the implicit function theorem, right? So that means that so basically what this is telling you, is that the implicit function theorem could be reread this way. If if A is regular, then this level set is locally a graph, right? It might not be globally a graph. You might not be able to describe the entire set as the graph of a single function, but near every point on that surface you can define a function that realizes that surface as a graph in a neighborhood of that point, right? So think about the sphere. You can't write the sphere globally as a graph, but any piece of the sphere can be expressed as a graph. All right? This is what the implicit function theorem is telling you. Okay, just to finish off, there is a generalization here, oops, I don't know what happened here. All right, that's supposed to be x, y. So the way you can generalize is these were equal to 1 before, so you consider values of k now possibly bigger than or equal to 1, and you consider functions from Rn plus k into Rk, and you think of that Rn plus k as splitting it up into the Rn part and the Rk part. And so then for values a in R sub k, you can consider the pre-image, and this guy here is going to be essentially n. It's going to be sort of an n-dimensional subset of Rn plus k. Or if you like, you could also say, well, it has codimension. You could say, how far away is it from the kind of the full dimension? It's codimension k, right? The dimension is k less than the space that it's sitting inside of. And so this condition that, saying f of x y equals a, if you consider that sort of component-wise, you can view this as a system of equations, right? So you're trying to kind of apply the implicit function theorem now not just to a single equation, but to several equations and several variables. And what you do in this case is you consider, again, think of this as a partial derivative, right? It's the derivative matrix, but it only includes the derivatives with respect to the y variables, and there are going to be k y variables, y1 up to yk. We have k components, f1 up to fk for our function, so you get a k by k matrix, right? It's a square matrix. And so the condition that is equivalent to the derivative being non-zero, that final partial derivative being non-zero, the equivalent condition here is that this matrix should be invertible. And we know that invertibility of this matrix corresponds to having a non-zero determinant, and so then everything kind of goes through the same as before, only now instead of 1 over a partial derivative, it's 1 over the determinant. It's essentially 1 over a Jacobian, if you like, and you get this formula relating the partial derivatives the same as before. Okay, so that's the implicit function theorem. We'll stick to the video, and that way we can start talking about vectors as differential operators tomorrow in class.